Hello, everyone. Welcome to AAE 364. In this lecture, we will look at how to design a controller using root locus. And let's first begin with an exercise. In this exercise, we are asked to verify whether a proportional controller or simply a P controller can enable the closed loop system shown here to meet the specifications, which are a settling time of less than 1 second and a percent overshoot less than 5% under a unit step reference input. And to do so, let's first note that the transfer function of the closed loop system is given by 10k over s squared plus 4s plus 10k, which is an underdamped second order system without zeros when the gain k equals to 1. Next, let's recall from topic 3 that the transient response specifications of an underdamped second order system without zeros can be completely determined by its pole locations. For example, the 2% settling time depends only on the real part of its poles, and the percent overshoot depends only on the damping ratio. Therefore, instead of thinking about settling time and overshoot separately, we can think of them as constraints on where the closed loop poles are allowed to be. And now to make sure that we're all on the same page, let's see how the specifications in this exercise can be converted into constraints on the closed loop pole locations. And let's begin with the settling time requirement. Since the settling time must be less than 1 second, the closed loop poles must have real parts less than -4. Next, let's consider the overshoot requirement. For the overshoot to be less than 5%, the damping ratio must be larger than 0.6901, or equivalently, the closed loop poles must lie within 46.36 degrees of the negative real axis. And now let's visualize these constraints on the complex. The blue dashed line corresponds to the settling time requirement, which requires the poles to lie to the left of the line. And the orange line corresponds to the damping ratio requirement, which requires the poles to lie within 46.3614 degrees to the negative real axis. And at this point, it should be clear that to satisfy the two specifications at the same time, the closed loop poles must remain inside these two lines. And the green shaded area here represents all accepted pole locations. And now comes the main takeaway. Instead of asking, can the controller help satisfy the settling time and overshoot specifications? We can ask a completely equivalent question, which is, can the controller move the closed loop poles into this green region? And once we know how the poles move as we tweak the gain value, controller design becomes a geometry problem on the complex plane. And that is exactly what root locus allows us to do. So now let's overlay the rule locus on the same plot. Recall that changing the proportional gain k changes the locations of the closed loop poles, and those trajectories are precisely the rule locus. And by looking at the plot, we can see that the rule locus never enter the green region. Therefore, no matter how we choose the proportional gain, we cannot satisfy both specifications simultaneously. And this naturally leads us to the next question, which is, if a proportional controller isn't enough, what kind of controller should we use instead? And before we answer this question, let's take a look at another exercise first. In this exercise, we are given the unit step response of the uncompensated closed loop system shown here. And by uncompensated, it means that no compensator has been added yet. So the controller is simply equal to 1. Also notice that the open loop transfer function in this case is of type 0 because it has no poles at the origin. And finally, from the figure shown here, we can see that the system has a peak time around 0.25 seconds, a percent overshoot around 60%, and a steady state error around 12%. And now we are asked to verify whether a P controller can help the closed loop system reduce its steady state error to less than 5%, while preserving the original transient response, especially the peak time and overshoot. And to do so, let's recall from topic 6 that for a type 0 system, the steady state error to a unit step input is inversely proportional to the position error constant, which is equal to 7.5K in this case. So from here, we can see that the steady state error can be easily reduced by increasing the gain K. However, this comes with a trade-off. As we increase the gain, the closed loop poles move along the rule locus. And in this system, they move vertically, which increases the imaginary part while leaving the real part nearly unchanged. As a result, the oscillation becomes faster and the overshoot also increases, as shown in the step response on the right. Therefore, a P controller cannot improve the steady state accuracy while preserving the original transient response. And this again naturally leads us to the same question. If a P controller isn't enough, what kind of controller should we use instead? And to answer this question, we will first introduce several commonly used controllers and compensators. Specifically, the PD controller and lead compensator are mainly used to improve transient response. On the other hand, the PI controller and lag compensator are mainly used to improve steady state accuracy. And if we need to improve both the transient response and the steady state performance, we can use either a PID controller or a lead lag compensator. Over the next few slides, we will take a closer look at each of these controllers before learning how to design them using the rule locus. And let's begin with the most well-known controller, the PID controller. The transfer function of a PID controller consists of three terms, and each term contributes differently to the system behavior. And later we will see how they can be interpreted from the rule locus perspective. But before we get into that, let's first see where this controller gets its name from. To see how, let's first recall from the block diagram that the Laplace transform of the control signal is simply the product of the controller transfer function and the Laplace transform of the error signal. And if we substitute the transfer function of a PID controller, we will obtain these three terms. And finally, taking the inverse Laplace transform gives us its time domain expression. And as you can see, the first term is proportional to the current error. The second term integrates all past errors. And the third term takes the derivative of the error. And this is exactly where the name comes from. The proportional term, the integral term, and the derivative term, or simply the PID controller. Now, let's take a look at several common controllers in the PID controller family. If we keep only the proportional term, we obtain the P controller, which we have already studied previously in topic 7. And if we keep the proportional and derivative terms, we obtain the PD controller. And notice that it can also be written as a gain multiplied by a 0. Similarly, if we keep the proportional and integral terms, we obtain the PI controller. And notice that it can also be written as a gain multiplied by a pole at the origin together with a nearby 0. Finally, notice that the PID controller can also be rewritten as a gain multiplied by a pole at the origin and 2 zeros. This also means that it can be viewed as the product of a PI controller and a PD controller. And this factorization will be especially useful for rule locus design. Now let's move on to another commonly used family of controllers, the lead lag compensators. And to help you understand how they got their names, we need to briefly preview or look at the frequency response of LTI systems, which is a topic that we will study later in topic 9. For now, just take the following result for granted. When a sinusoidal input is applied to a stable LTI system, the steady-state output is still going to be a sinusoid. However, its amplitude may change, and it may also be shifted forward or backward in phase. Specifically, If the phase shift is positive, then the steady state output is shifted forward in time relative to the input. And we will say that the system introduces a phase lead at that frequency. For example, in the graph shown here, we can see that the output reaches its peak slightly earlier than the input, which indicates that the system introduces a positive phase shift or phase lead at frequency of 1 radians per second. On the other hand, if the phase shift is negative, then the steady state output is shifted backward in time relative to the input. And we will say the system introduces a phase lag at that frequency. For example, in the graph shown here, we can see that the output reaches its peak slightly later than the input, which indicates that the system introduces a negative phase shift or phase lag at frequency of 1 radians per second. And now we can see how they got their names. A lead compensator is simply a system that introduces phase lead over a certain frequency range. And you can see that it contains of a gain, a zero, and a pole, with the pole located further to the left than the zero. On the other hand, a lag compensator introduces phase lag over a certain frequency range. And it also consists of a gain, a zero, and a pole. But the pole and zero are placed close together with the pole closer to the origin. Finally, by combining a lead compensator and a lag compensator, we obtain a lead lag compensator, which introduces phase lead over one frequency range and phase lag over another. In the last part of this lecture, we introduced several types of controllers that can be used to meet the design specifications. In the second part of this lecture, we will see how to design them systematically using the root locus method. Let's now revisit the first exercise from the previous part. Recall that we previously identified the feasible region that satisfies the design specifications. And since any point within this region meets the requirements, I've chosen one pair of desired dominant poles within this region as shown here. Therefore, our goal now is to design a controller that places the dominant close to poles at these locations. But before that, let's first ask the simplest question. Can a P controller do the job? And to answer this question, let's apply the phase condition. Notice that with the P controller, the open loop transfer function has no zeros and two poles, one at the origin and one at -4. And by adding up the phase contributions of these poles, we can see that the phase of the open loop transfer function at the desired closed loop pole S1 is equal to -4.7134 radians, which is equal to 1.5698 radians in modulus 2 pi, which is obviously not equal to pi. So the phase condition is not satisfied, and the desired closed loop poles are not on the root locus. And therefore, the P controller cannot achieve these specifications. From the previous analysis, we found that a P controller fails because of phase deficiency. In other words, the open loop transfer function does not provide enough phase at the desired pole location. And the missing phase is simply pi minus the phase of the open loop transfer function at the desired pole location, which is equal to pi over 2 in this case. And this naturally leads to the following question. What type of controller can introduce additional positive phase? Two common choices are a PD controller, which adds 1 0, and a Lie compensator, which adds both a 0 and a pole. With the pole further to the left than the 0. And to see how, let's first start with a PD control. With the PD controller, we can introduce one additional 0 into the open loop transfer function. And recall that a 0 contributes positive phase. So by placing the 0 at an appropriate location, it can provide the missing phase needed to satisfy the phase condition. And this reduces the controller design problem to a simple geometry. Where should we place the 0? From our previous analysis, we know that the PD controller 0 must contribute exactly the missing phase so that the phase condition can be satisfied. And since we already know the desired pole location, the amount of missing phase, and that the 0 must lie on the negative real axis, we can simply substitute these values into the equation shown here. And after doing so, we can see that the 0 should be placed at -6. And once the location of the 0 is determined, we are left with only one unknown, the gain k, which can be determined by the magnitude condition. And since the open loop transfer function L is the cascade of the PD controller and the plant, we can simply substitute these expressions into this equation shown here and evaluate them at the desired pole location. And after doing so, we can see that the gain should equal to 0.8. Therefore, the final PD controller consists of a gain of 0.8 and a 0 at -6. Finally, let's verify the controller's performance through a numerical simulation and see whether it satisfies the design specifications. According to the simulated unit step response shown here, you can see that the closed loop system now has an overshoot of about 3.8%, and a settling time of about 0.67 seconds. And since they both satisfy our original design specifications, we can conclude that PD controller design is successful. Next, let's move on to the lead compensator. Unlike the PD controller, the lead compensator contains a zero and an additional pole. And although the pole contributes negative phase, it's placed further to the left than the zero. As a result, its negative phase contribution is smaller than the positive phase contributed by the zero. Therefore, the compensator provides a net positive phase, which can provide the missing phase needed to meet the phase condition. And just like the PD controller, this reduces the compensator design problem to a simple geometry problem. Where should we place the zero and the pole? And again, unlike the PD controller, we now have one equation with two unknowns, the pole location and the zero location. This means that there are infinitely many possible solutions. And here, just to illustrate how it works, let's choose one such that the zero contributes a phase of 2.5 pi over 4. And the pole contributes a phase of 0.5 pi over 4. And notice that their difference is exactly pi over 2, which is the missing phase needed to meet the phase condition. And since we already know the desired pole location, the zero and pole must lie on the negative real axis and the phase they each contribute. We can simply substitute these values into the equations. And after doing so, we can see that the zero should be placed at negative 4.5668, and the pole should be placed at negative 14.3532. And just like before, once the locations of the pole and zero are found, we can determine the corresponding gain using the magnitude condition. And by substituting the compensator and the plant into the equation and evaluate them at the desired pole location, we can see that the corresponding gain should be 6.6825. Therefore, the lead compensator consists of a gain of 6.6825 and a zero at negative 4.5668 and a pole at negative 14.3532. Finally, let's verify the compensator's performance through a numerical simulation and see whether it satisfies the design specifications. According to the simulated unit step response shown here, we can see that the closed loop system now has an overshoot of about 3.3% and a settling time of about 0.86 seconds. And since they both satisfy our original design specifications, we can conclude that the lead compensator design is successful. And now, before we move on to the next exercise, I want to point out a few things. If the closed loop system happened to be an underdamped second order system with no zeros, then its poles completely determine the transient response. This idea also extends to many higher order systems. If a higher order system can be approximated by a second order system with no zeros, then its transient response is largely determined by its dominant poles. However, if the closed loop system contains zeros, the poles alone are no longer sufficient to accurately predict the transient response. In that case, we use the dominant poles to obtain an initial controller design and then validate the design by simulating the closed loop response. Now, let's revisit the second exercise from the last part of this lecture. In this exercise, we are given an uncompensated system whose transient response is already satisfactory. Therefore, instead of improving the transient response, our goal is to design a controller that reduces the steady state error while preserving the original transient response characteristics, especially the peak time and also the maximum overshoot. And this brings us to the following question. What type of controller can improve steady state accuracy without significantly changing the transient response? Two common choices are a PI controller, which adds a pole at the origin and a nearby zero, and a lag compensator, which adds both a pole and zero near the origin, with the zero located further to the left than the pole. And to see how, let's first start with the PI controller. With a PI controller, we can introduce a pole at the origin and a nearby zero into the open loop transfer function. And notice that the pole at the origin increases the system type by 1, and thus allows us to eliminate the steady state error. However, as you can see in this graph, this added pole also changes the shape of the root locus, which may significantly affect the transient response. Therefore, to preserve the original transient response, we place a zero close to the added pole so that its effect on the root locus is largely canceled. As a result, the root locus of the PI compensated system becomes much closer to that of the original system, as you can see in these two graphs. And this is exactly the design philosophy of a PI controller, which is to increase the system type while keeping the overall shape of the root locus nearly unchanged. And since there are infinitely many possible locations for the controller zero, here we simply choose one at -0.1. And notice that in this case, the compensated and uncompensated root locus are almost identical. Therefore, it is reasonable to assume that the original dominant poles are also on the root locus of the compensated system. And as we will see in the next slide, this assumption will help us to find the remaining unknown, which is the gain K. Since the open loop transfer function L is a cascade of the PI controller and the plant, and the original dominant poles are assumed to be on the root locus of the compensated system, we can substitute these expressions into the magnitude condition and evaluate them at the original pole location. And doing so will give us the gain of 1.0026, which is almost 1. And this is expected because the PI controller was designed to have only a minimal effect on the original root locus while increasing the system type. Finally, let's verify the controller's performance through a numerical simulation and see whether it satisfies the design specifications. According to the simulated unit step response shown here, we can see that the closed loop system now has 0 steady state error. And when we zoom in on a shorter interval, we can see that the peak time and maximum overshoot are almost identical to those of the uncompensated system. And since both of the specifications are met, we can conclude that the lag compensator design is successful. Next, let's move on to the lag compensator. With the lag compensator, we can introduce a pole and a zero, both near the origin, to the open loop transfer function, with the pole closer to the origin than the zero. And just like the PI controller, the pole and zero are placed close to each other so that their effect on the shape of the root locus is minimized. However, unlike the PI controller, the lag compensator cannot increase the system type to eliminate the steady state error. Instead, it reduces the steady state error by increasing the static error constant. To see how it works, notice that the uncompensated system has a position error constant of 7.5. And with the lag compensator, this constant is scaled by the factor k times the ratio of z to p. And since the pole and zero are placed very close to each other, they have a minimal effect on the root locus. As a result, the gain k remains close to 1. And the scaling on the position error constant is mainly determined by the ratio of z to p. Finally, because the zero is placed further to the left than the pole, the ratio is greater than 1, which allows the lag compensator to increase the position error constant and thus reduce the steady state error. And now let's determine how large the ratio needs to be to meet the specifications. Recall from topic 6 that for a type 0 system, the steady state error to a unit step input is inversely proportional to the position error constant. Therefore, to ensure a steady state error of less than 5%, the position error constant must either be greater than 19 or less than -21. And from our previous analysis, we can see that the constant must be positive in this case. So let's focus on the case where the constant must be greater than 19. And from here, we can see that to meet the specifications, The ratio has to be greater than 19 over 7.5, which is approximately 2.5333. And again, just like the PI controller, there are infinitely many choices of the locations of the pole and zero. And here, just to illustrate how it works, let's consider one such that the zero is placed at negative zero point 0.1 and the pole is placed at negative 0.02. And in this case, the ratio of z to p is 5, which is twice as much as we needed. And again, notice that this choice ensures that the root locus of the compensated system closely matches the uncompensated one. Therefore, it is reasonable to assume that the original dominant poles are still on the root locus of the compensated system, which will allow us to determine the controller gain using only the magnitude condition. Again, since the open loop transfer function L is a cascade of the lag compensator and the plant, and that the original dominant poles are assumed to lie on the root locus of the compensated one, we can substitute these expressions into the magnitude condition and evaluate them at the original pole location. And doing so will give us the gain of 1.0021, which is almost 1. And this is again expected because the lag compensator was designed to have only a minimal effect on the original root locus while increasing the error constant. Finally, let's verify the compensator's performance through a numerical simulation and see whether it satisfies the design specifications. According to the simulated unit step response shown here, we can see that the closed loop system now has a steady state error of roughly 3%. And when we zoom in on a shorter interval, we can see that the peak time and the maximum overshoot are almost identical to those of the uncompensated system. And since both of the specifications are met, we can conclude that the lag compensator design is successful. And now before we move on to the next exercise, I would like to point out one thing. Although we place the controller zero very close to the added pole so that their effects nearly cancel. This cancellation, however, is never perfect. As a result, compared to the uncompensated system, there will be an additional slow closed-loop pole near the origin, and the transient response may still change slightly. Specifically, while the peak time and maximum overshoot are usually preserved quite well, the settling time is often more sensitive and may change noticeably. For this reason, after designing either a PI controller or a lag compensator, we should always verify the final performance through a simulation. Now, let's look at the last exercise. In this exercise, our goal is to design a controller that satisfies both the transient response and steady state specifications. And from the previous two exercises, we already know how to address each of these requirements individually. A PD controller can be used to achieve the desired transient response by placing the dominant closed loop poles at the desired locations. while a PI controller can be used to eliminate the steady-state error by introducing integral action. Therefore, by combining a PD controller with a PI controller, we can obtain a PID controller that can satisfy both the transient response and steady-state specifications. And since the design procedure is essentially the same as what we covered in exercises 1 and 2, I will leave this example for you to work through on your own. And now, to wrap up this lecture, let's summarize the main ideas behind controller design using rule locus. The first step is always to translate the design specifications into constraints on the desired closed-loop pole locations, system type, or static error constants. Next, we see whether a simple P controller is sufficient to satisfy these requirements. And if a P controller is not sufficient, which is usually the case, we then choose a controller based on which requirement is not satisfied. If the problem is poor transient response, we can use a PD controller or a lead compensator. These controllers introduce phase lead, shifting the rule locus so that the desired dominant closed-loop poles satisfy the rule locus phase condition. On the other hand, if the problem is poor steady-state performance, we can use a PI controller or a lag compensator. The PI controller increases system type, while the lag compensator increases the static error constants. And both are designed to preserve the original rule locus as much as possible. Finally, if both transient response and steady-state specifications must be satisfied simultaneously, we can use a PID controller, which combines a PD controller with a PI controller, or a lead lag compensator, which combines a lead compensator with a lag compensator. And regardless of which controller we design, the final step is always the same. We verify the design through simulation, compare it against the specifications, and refine the controller if necessary.